okay?
Yes.
Dear participants, I have pleasure to present you results of our investigation. Its work has been done in frame of collaboration with the Polish Academy of Science and Vernadsky Institute of General and Inorganic Chemistry. This work was done about core shell exchange coupled nanoparticles. Its materials are very promising for hyperthermia treatment. For this investigation, we made the magnetic nanoparticles. Oh, sorry. Yes. We made the pure magnetic nanoparticles and cobalt ferrite nanoparticles. Its initial samples. The next samples is the mix with these nanoparticles, and the last samples is the core shell nanoparticles with the magnetic core and cobalt ferrite shell. The aim of these nanoparticles is understand how influence of exchange and dipolar interaction on the heating efficiency and magnetic nanoparticle properties of these systems. But firstly, I will talk about hyperthermia treatment. Hyperthermia is one of the most perspective methods in the oncology. In ideal hyperthermia, the cancer it should destroy the cancer cells without damage the surrounding health tissues. It involves the delivery of magnetic nanoparticles to the tumor site. Sorry. And after that, we use alternating magnetic field, which calls to heating of nanoparticles. The cancer cells die in temperature in range from 41 to 47 Celsius. This presents the nude mice xenograft, and this you can see the cancer before treatment and without treatment after 18 days, and with core shell nanoparticles. The heating of nanoparticles make when the magnetic moment of nanoparticles is rotate, and we have two possibilities of mechanism relaxation in superparamagnetic nanoparticles. It's Brown relaxation when the whole nanoparticles is rotate in fluid. But the magnetic moment in the nanoparticles is fixed along the crystal axis. The heating of nanoparticles is due to share with fluids. And when the magnetic moment of nanoparticles is rotate, but the nanoparticles itself fixed, it means that nanoparticles undergo the Néel relaxation. In this situation, the thermal energy is dissipated by the rotation, by the rearrangement, the atomic dipolar moment within the crystals. Heating is a quantity which depends on the properties of nanoparticles. It's such as mean size of nanoparticles, saturation magnetization, magnetic anisotropy, interparticle interactions, also as well as the alternating magnetic field amplitude and frequency. There are many materials was investigated for the perspective in hyperthermia treatment, but the last many attention paid to the core shell nanoparticles, which consist of with magnetically hard and magnetically soft materials. It allowed to increase the anisotropy constant and obtain the high magnetic, the high magnetization. For this reason, to obtain the new core shell nanomaterials for the hyperthermia treatment, we synthesize the nanoparticles with magnetically soft core and magnetically hard shell, use precipitation from non-aqueous solution in organic atmosphere. Additionally, these nanoparticles was covered by the organic shell, which prevent they to agglomerate. In results, we obtain the four kind of nanoparticle system. It's cobalt ferrite nanoparticles, manganese nanoparticles, mixed from this first and second nanoparticle system, and core shell nanoparticle system. The mean size was estimated from the TEM measurements. The nanoparticles mostly are sphericals. From XRD measurements, we can see that the nanoparticles are crystalline, and the diffraction peaks is typical for the respective samples. Let's start now talk about the magnetization measurements. All magnetization measurements was done used the physical property measurement system PPMS produced by Quantum Design. In this picture we can see the hysteresis loops. The red loops is the cobalt ferrite nanoparticles, is the hard ferrite magnetic material with high coercitivity and with high magnetization, but for cobalt ferrite this magnetization is significant decrease when they decrease the size of nanoparticles. It's due to the content of the spins on the surface of nanoparticles. In opposite, the green loops is the manganese, is the soft magnetic materials without coercitivity and with high magnetization, and this magnetization is not significantly decreased when we decrease the size of nanoparticles. And the next two loops is mixed samples and core shell samples. Also, we calculate the anisotropy constant, use this equation, and how we can see the smallest value obtained for the ferrum manganese nanoparticles, the higher for the cobalt nanoparticles, what is predicted. But very interesting, the maximum value we obtain for the mixed and core shell nanoparticles, and this we have a similar value. What is very interesting in this? In the mixed nanoparticles, because it's a very different system. In mixed nanoparticles, we have only the dipole-dipole interaction between the magnetically soft nanoparticles and magnetically hard nanoparticles. And in the core shell nanoparticles, we additionally have exchange coupled between core and shell. And how you can see this exchange coupled not influence on the anisotropy constant or on the some magnetic parameters on the hysteresis loops on the magnetic systems. To investigate the temperature magnetization dependencies of these samples, we use a simple procedure which is so-called zero field cooling and field cooling cycles. For samples, we have a maximum on the ZFC, and we have temperature irreversibility, after which in lower temperatures the branches are separated. This behavior is typical for the single domain nanoparticles. In this picture we can see the dependencies of the blocking temperature versus mass ratio of the cobalt ferrite and manganese nanoparticles. It's well known with the increase the nanoparticle size, the blocking temperature shift to the higher temperature. But in our case, the size of manganese bigger than the size for the cobalt ferrite, but the value of blocking temperature is smaller. It's due to the cobalt ferrite nanoparticles have a higher anisotropy constant. Higher value we obtained for the mixed nanoparticles due to a dipole-dipole interaction, and the max value we obtained for the core shell nanoparticles due to exchange coupled between core and shell. To investigate the dynamic properties of the system, the ISS susceptibility measurements was done. On this picture, we presented the detailed investigation of the magnetic nanoparticles in the frequency from 45 kHz to 10 kHz. The amplitude of the real peak decrease, whereas the amplitude for the imagined component increase with increasing frequency. And on these pictures present real and imaginary part for all samples at 200 kHz. And these AC peaks of the samples are consistent with the peaks of ZFC curves. And this temperature dependence, frequency dependence temperature peaks was analyzed, used the Arrhenius, Vogel-Fulcher, and Pavlo law. Arrhenius law used for the superparamagnetic nanoparticles. In this system between nanoparticles, the interaction is absent. And we obtain the next value. Tau zero is the characteristic relaxation time. This is the energy barrier. And we obtain the physically small and physically high value for the Arrhenius law for all samples. It means that in this system presents some dipole interactions, and it points to a spin glass behavior. Then we use Vogel-Fulcher law and Pavlo law. This system used for nanoparticles with some interactions, and we obtain a physical mean and physical reasonable value for all samples. And this means that we have two possibilities. It can be a progressive inhomogeneous freezing or thermodynamic phase transition to spin glass state. To answer of this question, we use these two empirical equations, and obtained parameter is typical for inhomogeneous freezing to spin glass-like state. And for the most interesting is the result of the heating of nanoparticles. For obtaining this, we use the magnetic field frequency at 300 kHz with the magnetic field strength 7.7 kA per meter. And how we can see from this picture, the little value for the pure manganese and cobalt ferrite nanoparticles, but very significant increase in the mixed nanoparticles due to dipole-dipole interaction, and the highest value we obtain for the core shell nanoparticles. What is very interesting that magnetic anisotropy and saturation magnetization are not the main factors which influences the heat efficiency.